If you can code it, it's more real than it may be seemed at first. In fact, it is real in a sense, because you can play with it. What you are seeing on the screen right now is a map of a strange and interesting surface called the Hyperbolic Plane. After this video is over, you'll have the knowledge to understand and code some of the things you're seeing. And after the next one, everything that you see on screen will be within your reach, like placing and moving objects in the surface at your will. Feel it really deserves to be called plane.
Because it does. It's very similar to the normal Euclidean plane. For instance, despite the finite look of the map, the hyperbolic plane has infinite area. It's just that, in this specific map of it, length gets compressed as you approach the boundary. Yes, maps of the hyperbolic plane are weird.
And stuff gets even weirder when we look at how the hyperbolic plane is different than the Euclidean plane. For example, take a straight line and take a point outside that line. Now all of a sudden you can have multiple, in fact infinite, straight lines that pass through the same point and don't touch your line. If you heard the term non-Euclidean before, you might have seen it attached at spaces that present weird behavior like this. Maybe we even heard about how the more than one parallel line property was the very reason that made humanity discover the geometry that happens in the hyperbolic plane. In fact, a way of making sense of what's happening here is saying, hey, I define this pole to be my space, these circles to be my lines, and regular angles as my angles. They satisfy all hyperbolic geometry axioms. So voila, now we have the geometry. Well, yes, and this way of doing things is what motivates mathematicians to refer to a map of the hyperbolic plane as model for hyperbolic geometry. But this feels unsatisfying, arbitrary. Makes the hyperbolic plane, the surface behind it all, seem like a complete mystery. And yes, it is weird. We haven't even shown a picture of the actual hyperbolic plane so far, and that's for a good reason that we'll discuss later. But nonetheless, you can understand a lot more. So, in this video we take the long route. We'll construct the hyperbolic plane from the ground up. There are many ways to do this, and we'll be mentioning some others at the end of the video, but we'll choose one that goes from the familiar to the unfamiliar, that makes us understand along the way how we can do geometry on curved surfaces. And for that, we need to talk about... We live most of our lives bound to the surface of a sphere. We say most because one can still jump, make tall buildings, dig holes, etc. Our world is still three-dimensional, but we are now interested in studying what happened just on the surface of the sphere, as if things that live on said surface were literally embedded on it. No jumping, no digging. This will make the geometry we study two-dimensional, because despite the sphere sitting on a three-dimensional space, objects that live on the surface of the sphere have just 2 degrees of freedom to move. So, under those constraints, how can we do geometry? We already have points, all of those on the surface of the sphere. We need straight lines. But wait, because the sphere is curved, any straight line that we draw leaves the surface, and we don't want that. So, we have to go a bit more abstract. What defines a straight line on the Euclidean plane? Well, we can go at least 3 different routes here. We can say that because we don't have properly straight lines in this context, of all the lines we have, we'll just take the straightest. We can say that a line is just defined as the curve fixed by a reflection. Or we can take a more natural but indirect approach and say that a straight line segment is the curve that gives the shortest path between 2 points, and extend our definition from there to the whole line. These 3 seem very different, and it's not clear that they will give the same curve on the sphere, but in fact they are equivalent. And it turns out that the curve that satisfies these three definitions on the sphere is a great circle, that is, a circle with the same radius of the sphere.
By the way, a curve analogous to a straight line but for a specific surface is called geodesic.
Now let's define angle.
This one's easy. Take two geodesics that intersect. Now take the tangent of both at the point of intersection. Then the angle between the geodesics is the angle between those tangents. But this feels kind of like cheating. Aren't we leaving the surface to do this? Well, not really. We are showing the two whole tangent lines, but because angle is a local property, to measure the angle between them, you just need a tiny bit of the tangents near the point. In fact, it's enough with any tiny bit, no matter how tiny.
And because when the tangents get smaller and smaller, they become indistinguishable from the curve. Beings living on the surface can measure the angle without leaving said surface, just zooming in. So, no real problem here. And now we have points, lines, angles. We can make a triangle. In fact, we can make a polygon of any number of sides. We can even make a polygon of two sides, which hints at the weirdness of the geometry.
And now that we have geometric figures,
we might be more comfortable calling this the way of doing geometry. But we are not ready yet to talk about the hyperbolic plane for reasons we'll discuss in a moment. We first need to talk about... Earlier, we said that the geometry we are working with is really two-dimensional. So, why do you need the 3D space to work on it? That's the neat part. You don't. The only thing you need is a map, with a tiny bit of extra information. But what is a map? Mathematically, well, a map represents a region S of the surface on a region E of the Euclidean plane. It does so assigning to each point of S a unique point of E. So, mathematically, a map is just a region of the surface, a region of the plane, and a bijective function between them. So, really, because the function is a variable, you have two functions there. A function that takes a point of the surface to the plane, called the chart, and a function that takes a point on the region of the plane and returns the corresponding point on the surface, called the parametrization. You've seen many of these before. This, for example, is called the Lambert cylindrical projection, though some folks prefer to call it the Archimedes projection. The formulas of the chart and the parametrization are these, by the way. The path we take into the hyperbolic plane uses a map as a tool, but one that's weirder than this, in some ways at least. Its chart is defined as follows. Take the unit sphere, centered at the origin. Now if you want to know where a specific point of the sphere ends up in the new map, take the line that forms between that point and the north pole of the sphere, and look at where it intersects the XY plane. That's the location on the map. Our map appears then when we do this for every point of the sphere. It's an infinite map of a finite surface. Anyways, when you make the calculations, the formula for the chart is this, and the one for the parametrization is this. Now, a seemingly random question. If we have two curves crossing on the map, how do we calculate the angle they make on the real surface? You might be tempted to say, just measure the angle on the map, but that's not necessarily correct. For instance, back to the Archimedes projection. We can see that this corner of Canada gets really squished on the map, so we gotta be careful. One thing we could do is use the parametrization to find which curves they represent on the real surface and measure the angle the way we'd normally do here. And that would work, but we could do something better. Forget the sphere for a second. Take one of the curves. We know how to calculate the tangent at the point of intersection. Just take the derivative of the curve. We get the tangent vector at that point.
we don't need a full tangent line. Let's just work with the vector. We do the same to obtain the tangent of the other curve, but now before measuring the angle, we want to know which tangent vectors of the surface these tangent vectors of the map correspond to. Well, we can do this. Take the differential of the parametrization, evaluate it at the point of intersection, multiply each vector by it, and out there comes the tangent vectors in the surface. Please don't worry if you don't get why this works. These are advanced mathematics, but the short explanation is that a so-called differentiable function like this can be treated locally as just a linear function, and so the local properties of the input transform with just matrix multiplication. Anyways, now we can measure the angle between the vectors of the real surface using this property of the dot product. And that's it. But this way is more convoluted than the first one. What do we say is better? Because we just unlocked what is probably the most powerful tool of modern geometry. Let's look for a second at what we did. There's a thing that shows up a lot. This dot product of two vectors, each one multiplied by the differential. This operation is so common and useful that mathematicians call it the metric. Metric because it allows us to measure everything. If you are given the metric, you don't even need to know the chart of the parametrization. You don't even have to know which surface you are working on. If you draw two curves on the map, you can know the angle between them on the real surface, just with the metric as a black box. And it allows you to measure lengths of arbitrary curves as well, with a formula extremely similar to the one of the Euclidean geometry. You can even calculate areas, again without any other information. In conclusion, we can do everything we want in a geometry with just a metric and a regular plane. Going back to the stereographic projection for a second, its metric can be expressed after a little simplification like this. But this is just a regular dot product between the vectors of the map. So we can further simplify. The metric depends not just on the vectors of the map we give to it, but also on where those vectors sit on the map. But notice something, if we substitute this metric on the angle formula, things cancel out, and we end up with the formula for the angles between the vectors on the map. So we could measure the angles just in the map after all. Well, yes, but it's just because the stereographic projection has a very special property. Maps in which the angle between any two vectors in it is equal to the angle between the corresponding vectors in the surface are called conformal. The Archimedes projection is not conformal. As we saw earlier, the stereographic projection is. Now, one more thing that will be important later. We did the stereographic projection on the unit sphere to simplify a little, but later we'll need the formulas for the general sphere. So these are the chart, the parametrization, and the metric. Because the metric still is, at any particular point, just a constant multiple of the regular dot product. The map still is conformal. The real star of this chapter is the metric. And the reason is that it allows you to generalize. If we give a random function that satisfies a couple properties, and a region of the plane on which that function is defined, we can start doing geometry right away, treating the region as a map without even knowing in which surface we are working on. And this fact is going to be very useful for our purposes, because in the next chapter we will be. So, another sphere, show me the hyperbolic plane already. Well, about that, turns out there's a theorem that essentially says you can't have the whole hyperbolic plane in 3D. But as we saw at the beginning, we can still obtain and work with a map of it. Our hard work of understanding the sphere and its map is about to be crucial now. But first, only one ingredient is missing. We say we are studying the geometry that happens on curved surfaces. But how do we quantify curvature? There are a lot of definitions of curvature of a 2D surface, but today we just care about the Gaussian curvature. So, when we say curvature from now on, we mean specifically
Gaussian curvature. We care about that one specifically because it's an intrinsic property of the surface. That is, it can be measured by the beings embedded on it that have no idea of the space containing it. We will not get into details about its definitions though. All we care about today is the curvature of the sphere, which turns out is this. This formula implies that the curvature of the sphere is always positive. But check for a moment that the formula at least makes sense. Notice, for instance, that as the radius grows, the curvature approaches 0. And we end up having essentially a flat plane.
That's why flat earth.
Now, back to the main quest. How can we make a map of a surface that we cannot see? Well, remember that we don't need the surface really. We just need a region of the Euclidean plane and a metric. Now's when the magic happens. We saw that when we begin to grow a sphere, an object with positive curvature but finite area, we approach a plane, an object with zero curvature but infinite area. But what happens if we want more space? Okay, that's a strange statement. In the plane we have infinite space. What we just said has an exact meaning though, that we'll explain when we see later alternative constructions of the hyperbolic plane. But for the moment, let's just go with the motion so we don't distract ourselves and say that we just have to keep growing the sphere past the infinite radius. Yes, one strange statement after the other, but this time we will make sense of it right now. You see, you can't go past infinity without getting into trouble, but you can go below 0. We saw earlier that the curvature of the sphere only depends on its radius, but we can flip that statement. We can say that the radius depends on the curvature. Why would we do that? We still can't get to the negative curvature. Kappa is below a square root. Well, check this out. This was the metric of the stereographic projection, right? Look at what happens if we use this formula here. The square roots disappear, and in the perfect place. Remember that with the metric, one can do anything in the geometry. So we can now plug, for instance, -1 as kappa. But let's visualize what happens when kappa starts to go negative.
The plan is the following. We'll graph every circle at integer distance from the center of the surface. Show the map of the surface with the circles and all, and start reducing the curvature, which translates to growing the sphere at the beginning, but to go beyond the Euclidean plane and to negative curvatures, we'll have to drop the view of the sphere and go fully abstract. Our construction makes no sense in a 3D view, only in the map, and that's completely fine. Remember that the metric is all we need. Okay, ready? Go! So, this is weird. When the curvature turned negative, suddenly all circles appear to be confined. This behavior kind of makes sense, given that the metric, for a kappa value of -1, has a problem with you putting in a point at distance 1 on the Euclidean plane from the center. And if you can't reach there from the center, you can't reach outside the unit circle either. So yes, this is it. We have this covered.
This map is called the Poincaré disk model of the hyperbolic plane. Now let's explore it. First, as we said at the beginning of the video, this is a finite map of an infinite space. You can see it right here. We have an infinite amount of circles, all of them separated by 1 unit from the next. You can see as well that the length on the map that represents 1 unit on the hyperbolic plane gets smaller and smaller as we approach the boundary. Remember, we are rendering all this using just the metric. And if you look at the metric, you can see that in fact, the factor in front grows as we get farther from the origin.
Another thing that comes easily out of the metric is the fact that this map preserves the conformality of the stereographic projection. So measuring angles is easy. The angle in the map equals the angle in the surface. So we have points, angles. Where are the geodesics? Well, it's a little more convoluted to convince you about this fact, but in this map, the geodesics are represented by the circles that intersect the unit circle on right angles and the diameters of the unit circle, which you can consider as circles with the center at infinity. Now we have all the elements to do geometry, so we can make a triangle or any other polygon.
And if we use the formula for measuring length of curves to measure the length of the geodesic between 2 points, we suddenly have the formula for the distance between 2 points.
And to demonstrate what we can do with the tools we have now, if we put a couple thumbtacks on top of the map, pinning down some points, and color every point on the map according to the color of the nearest thumbtack, but measuring distance in the hyperbolic plane, we get a hyperbolic Voronoi diagram. And this is just the tip of the iceberg, but we are short on time, so let's finish things off seeing.
Now we want to address some confusion surrounding this, hopefully now less mysterious object that is the hyperbolic plane. Specifically about what objects are not the hyperbolic plane, but maps of it, or attempts to make sense of some of its weird properties. So this is not the hyperbolic plane. This surface is called the tractoid. Despite the fact that it does have constant negative curvature, it has the incorrect topology, so to speak. It has a boundary on one direction and loops around itself on the other. You can think about the relation of this surface and the hyperbolic plane as analogous to the one of the cylinder and the Euclidean plane. However, there's a construction of the hyperbolic plane similar in spirit to the one we did in this video that starts with the tractoid, makes a map of it, and extends it in two different ways to fix the problem that the tractoid has. You end up then with a different map of the hyperbolic plane. And yes, let's emphasize, it is the same hyperbolic plane we are talking about. You can even convert from this map to the one we ended up with earlier on the video. This new construction ends up showing that the tractoid can be interpreted as the inside of a kind of circle in the hyperbolic plane. This is not the hyperbolic plane. This is just another map of it. Just one that sits on 3D space. And as a map, you can measure distances and angles on it. Okay, if the metric used to do this was the normal Euclidean metric, we could call this the hyperbolic plane. Like we can call the sphere the spherical plane. But in fact, that's the point of failure. To measure distances and angles, we use metric called the Minkowski metric that has, by the way, connections with special relativity. This is not the hyperbolic plane. This one's very close though. You can see it as a patch of the hyperbolic plane, and it's beautiful, symmetric, but it has no equation. You can construct it in the physical world, draw accurate geodesics. You can even prove and calculate the constant negative curvature of the physical model, but has the disadvantage of being hard to use as a digital canvas. And you get in trouble if you try to extend it infinitely. This is obviously not the hyperbolic plane. It does use an interesting property of the hyperbolic plane though. That is the shape that you end up with if you try to, in a way, cram more space where they shouldn't be. Concretely, if you try to make a tessellation of the Euclidean plane with some polygon, but with more polygons around a vertex than the plane admits. Finally, you see sometimes people refer to the hyperbolic plane as a sphere of imaginary radius. That's just because when you isolate the radius in the curvature equation, you get that. So, by this point you're likely to have a nice understanding of what is and isn't the hyperbolic plane. If you don't, No worries, you can always rewatch the video later. It's a pretty damn long and dense video. And if you want to go into fine detail of the ideas shown in this video, you should go read the excellent course/book on Foundations of Geometry by Steve Trettel. In fact, the approach for getting to the hyperbolic plane that we took in this video is the one that this book takes. It's probably the most intuitive and friendly explanation of modern geometry you'll find on the internet. And it's for free. We'll have a link to it down below, as well as other excellent resources to learn about these topics. There are good resources for learning hyperbolic geometry. They are just very hard to find. So, we hope this video and the links we leave down there serve as a good reference to start learning about the subject. But there's something missing, of course. We have the hyperbolic plane with triangles and so on, but we haven't talked about the countless weird properties it has, nor have we talked about how to properly place and move an object in the hyperbolic plane. You know, coordinate systems, vectors, and so on. It's not as straightforward as you might think, but that we'll see in the next video.